2.4 Rates of Change in Tangent Lines, Part 1. Your objectives for this lesson are to find the slope of a curve at a point and to write the equation of a tangent line and a normal line. Okay, so average rate of change. This is something that we've talked about before. An average rate of change is equal to the amount of change over time. In terms of a graph, this would be delta y over delta x. Example 1. Find the average rate of change of f of x equals x cubed minus x over the interval 1, 3. So we've already established that we are looking for delta y over delta x. For here, f of x is the same as y, so we're going to have f of 3 minus f of 1, this is our change in y, over 3 minus 1. Now I'm going to do some side work over here in blue to figure out what f of 3 is. So we have 3 cubed minus 3, 27 minus 3, which is 24, and f of 1 is 1 cubed minus 1, 1 minus 1, which is 0. Okay, let's go back to the problem. So f of 3 we said is 24 minus 0 over 3 minus 1. 24 divided by 2 gives us an average rate of change of 12. So we don't actually have a unit here, but the number is 12. Example 2. This graph shows the growth of a fruit fly population in a controlled experiment. So you can see as time goes on, the population is increasing. And this says, use the points P located at 23, 150 and Q at 45, 340 to compute the average rate of change and slope of the secant line PQ. So a secant line is pretty simple definition. It's just a line that intersects the graph at 2 points. So this would be a secant line to this curve. You might remember secant lines from geometry talking about circles. So if this was your circle, a secant line is simply a line that intersects the circle at 2 points. So it cuts through the circle just like this line is cutting through the curve. But we want to compute our average rate of change. So again, we have delta y over delta x. So 340 minus 150 divided by 45 minus 23. This simplifies to 190 over 22, which is approximately equal to 8.6. So between P and Q, you're seeing an increase of 8.6 flies per day. Of course, you might be saying to yourself, you can't have 8.6 flies per day. You need a whole fly, so that would be about 9 flies per day, if you want to get technical. So this is our average increase on that interval. Okay, you may have noticed that the formula for average rate of change is in fact the slope formula. So remember, slope formula is delta y over delta x. This is the exact same formula that we've been using. So the average rate of change is indeed the slope of the secant line. This is important. You should remember this. Remember this. If you are trying to find instantaneous rate of change, The slope of the secant line approaches the slope of the tangent to the curve. What does this mean? Well, if I took this graph here and I wanted to find the rate of change at day 23 instead of over an interval, I would move my Q, I would choose a Q much closer to P than this one. And the closer I get to P, the more accurate the instantaneous rate of change I'm calculating is going to be. So this is when, before we were using the instantaneous speed formula, instantaneous rate of change, and you wanted to calculate like when h equals 0. So you're trying to get a very, very small distance away from P. So you're really closing that gap and honing in on this rate of change as opposed to the change on the interval. Pierre Fermat did some work on finding the slope of a curve at a point, and this is a short summary of that. So basically, the first thing you need to do is calculate the slope of a secant through P and Q nearby on the curve. That's what we just did with the fruit fly problem. Step 2, find the limiting value of the secant slope, if it exists, as Q approaches P along the curve. So calculating a limit. Step 3, the slope of the curve at P is defined to be this number, and we define the tangent to the curve at P to be the line through P with this slope. So the slope of the tangent line is the limit as Q approaches P, the limit of the secant line as Q approaches P along the curve. Example 3. Find the slope of the parabola y equals x squared at the point 2, 4. Write an equation for the tangent to the parabola at this point. So first thing I want to do is graph this. It's a pretty easy graph. This is our default parabola, we'll call it. So point at 0, 0 here, and 2, 4 would be like here. Okay, let me actually move this down just a little bit. Okay, and I'm going to plot another point here at 2 plus h. Okay, so we've moved h units further along the axis, and the y coordinate here is 2 plus h squared. Okay, so the first thing that I need to do is figure out the slope of the secant line passing through these 2 points. So this secant line right here, make this red. Okay, so the slope of this secant line. And that is delta y divided by delta x, which gives us 2 plus h squared minus 4 divided by 2 plus h minus 2. Okay, so let's simplify this. I know I need to expand this binomial, so I have 4 plus 4h plus h squared minus 4, and I can bust this out of the parentheses down here. Okay. These cancel, so do these. So I have 4h plus h squared all over h. The last thing I can cancel, there's an h common to all of these terms. So I really am just left with 4 plus h. This is my slope of the secant line. The next thing I need to do is find the limiting value of this slope as Q approaches P along my curve. So this is part 2. So we're going to say the limit as H approaches 0 of H plus 4. So this is from here. Just plopped that in there. And you know that the quick way to find this limit is to just plug in the 0. And we get 4. So the limit of this is 4. Okay? And therefore, the slope of the curve P, we said, is defined to be this number. So the slope of the secant line at 2, 4 is 4. So this is the slope at point P. Okay? The tangent to the parabola at P is through, so let's say tangent at point P passes through the point 2, 4, so that is P, and has a slope of 4. We can pretty easily write the equation of this line. Y minus y1 is mx minus x1. So we have y minus 4 is 4 times x minus 2. I'm going to move the 4 to the other side of the equation and distribute this 4 quickly. And we are left with y equals 4x minus 8 plus 4, or 4x minus 4. So this is the tangent line. So this is the equation of the tangent line at 2, 4. We actually did 2 things here. We did find the slope of the parabola at 2, 4, but then we took that a step further and actually turned this into the equation of the line tangent to the parabola at 2, 4, and this was that equation right there. So this is the end of part 1 of this lesson.